In this video, we got Momentum Worksheet 1, number 1. Let's get into it. Kim holds a 2 kilogram air rifle loosely so that the gun moves independently of the girl and fires a bullet of mass of 1 gram. The muzzle velocity, or the velocity of the bullet comes out of the muzzle of the barrel of the gun, is 150 meters per second. What's the rifle's recoil speed? Okay, let's do that first. So first, we can see that the firing is the action there. And so I'm going to be looking at both before and after we fire this gun here, this air rifle. So let's draw a picture. As always, we need an air rifle. So can you draw an air rifle? Can I draw an air rifle? That's a question. It's a rifle, so it's got some big long barrel there and like a little trigger in there. Maybe the trigger's got to be like attached to something. That's not so bad. Okay. She's got to be bigger than this thing. Okay, so she's holding it loosely. Notice I made like a little gap there, or tried to, so that it's not up against her shoulder as you normally would hold a rifle. And then we'll do it, we got to put the bullet in there as well. So I'll put the bullet inside of there, so I recognize that the bullet has yet to be fired. Maybe I'll even put a velocity there for the bullet is 0. And the velocity of the gun in black here is also 0. Therefore, I know that the momentum of the gun there is 0, since it's just mass times velocity there, and the momentum of that bullet there is also 0. Cool. I go and I draw another picture, and I'm going to go ahead and copy this picture for speed, and if you need more time drawing, well, that's pretty easy to just pause this video. Let's see if I can delete. Ooh, wow. I got that. Wow. And then the velocity and the momentum are a little bit different afterwards. You have the bullet come out of the barrel here, and we're gonna assume that the bullet, it's like the instant the bullet comes right out of the barrel, so we're not worried about like it slowing down from air resistance or anything like that afterwards. And so then afterwards we know that the velocity here is 150 meters per second, and the velocity of the gun itself we're not sure about. That's what we're trying to figure out here. Oh, okay. Well, let's go ahead and I'm thinking about momentum here because I have no motion in the before picture here, and it seems like I have real motion in the after picture here. Can I create motion? Can I create momentum? And the answer is nope, can't do that. So then what's going on here? Well, let's keep looking at momentum here. I'm going to go ahead and look at the momentum of this bullet here afterwards. I know that it's just any mass times velocity here. So I go look at the momentum of the bullet, and I see that the mass of that thing is 1 gram. Now, alarms are going off my head because when I see grams there, I go, wait, hold on, I need standard units, and gram isn't a standard unit. I need to take grams, and I got to convert them into kilograms. And I remember that there are 1,000 grams in 1 kilogram there. Kilo is a prefix for 1,000. If I can write kilograms there. And so I need to take that 1 gram and divide it by 1,000 there so I can get it into kilograms. Okay, cool. So now the mass of the bullet there is going to be, I move that decimal place over 3 places there, so it'll give me 001 kilograms for that mass there. So now I can go and actually put that in, and I get 0.001 kilograms multiplied by its exit velocity there, 150 meters per second. And now notice that I'm just dividing by 1,000 here, so I can actually do this in my head. So the decimal point's right there, and I just move it over 3 places there. So now I get 0.150. And notice the units here are for momentum. There's no like new unit for momentum, so it's just kilograms times meters, and then I have a per second. That's it. And notice it's not a per second squared there. I know we have often time talked about velocity, and so sometimes it's easy out of habit to just say, kilograms per meters per second squared, but it's just per second. Okay, so this means that the bullet has real motion, real momentum moving forward and to the right. And we'll say to the right is a positive value, as we normally do. So that means, well, how can I create? It sure seems like I created this motion or momentum going forward since I had no motion beforehand. Well, if I have something moving to the right afterwards, that means that I must also have something moving to the left afterwards. And this thing is going to have some velocity that is moving to the left, meaning that it's going to have some momentum then moving to the left there as well. And wait, if it's got a velocity to the left, that's going to be a negative velocity instead. And so that's going to be a negative momentum. And lo and behold, I can't create or destroy momentum. So if I looked at my system here, and if I included everything that's interacting here, that is exchanging motion here, then let's go do that. If I include both the we'll say just the gun and the bullet, I'm including everything that's transferring motion or momentum here. And so then if my system includes all of that stuff, then I know that the change in momentum of everything there, you could say the entire universe, if I can spell universe, or really in this case, it's just the gun and the bullet, must be equal to 0, meaning that the momentum beforehand must be equal to the momentum afterwards. And we already saw that the momentum beforehand was just the momentum of that gun beforehand plus the momentum of that bullet beforehand, and both of those were 0. Okay, so then the momentum beforehand must be equal to the momentum afterwards. The momentum afterwards, what's that? Well, it's the momentum of that gun afterwards plus the momentum of that bullet afterwards. Why are there only 2 objects? Well, because there's only 2 objects interacting here. If there was 3 or 4 or 7, you'd just have 7 different things that you're adding momentum together. And we already now know that the momentum of that gun there is 0.150 kilograms meters per second. So therefore, what value must this gun be? Well, you're right. That gun must have a value of negative 0.150 kilograms meters per second. Oh, I got a little bit small there. I should have made my box bigger. I'll go ahead and make that bigger just so it's easier for you to read. Kilograms meters per second. All right, so it's got to have that. Well, let's kind of keep working backwards here. I know that momentum, as we did before, was just the mass of that gun times the velocity of that gun there, and now it's equal to that bit there. Well, do I know the mass of that gun? I'm going to go ahead and I'm going to break it out, and I'm going to write it as a separate equation off to the side here. So the momentum of the gun is equal to the mass of the gun times the velocity of that gun. And so the momentum is negative 0.150, we said. I'll drop the units here just for simplicity's sake. The mass of that gun, I think it said it was 1 kilogram, did it not? 2 kilograms. 2 kilogram gun there, and now it's multiplied by some velocity. Well, let's go and solve for the velocity. That's pretty easy. So the velocity of that gun, I'm just dividing by 2, so I got 15 divided by 2, which is 7.5, and I got to put a decimal place in there, so that's going to be 0.75, and that's still a negative. And if we looked at the units, I'd have kilograms meters per second here, and divided by kilograms, and so I actually get meters per second. Maybe I should show that in a different color here. And we would have, separate from this, we just had kilograms meters per second, which was that 0.15. And then I went and I divided by a kilogram, which is the same thing as multiplying by 1 over the kilograms there. And we can see that the kilograms cancels out, and it's kg, it cancels out there. And so I'm left with just meters per second, which is exactly what velocity is. Now the velocity came out to be negative. Is that a problem? Well, no. With a velocity negative, that's just moving to the left, and that's what we predicted, that it would kick back and then probably run into this person and bruise them, and that's why you don't hold it loosely like this, but you hold it right up against your shoulder, so that it doesn't get moving really fast and then run into you, but instead, as it starts to speed up, if it's right against your body, then as this gun starts to speed up, well, your body then must speed up directly with that. So it's not this big force right away, but instead it's slowly speeding your body up and it doesn't hurt as much. Okay, so that means that we just solved this, that the velocity here, and I did that off to the side, the velocity of the gun is that velocity right there. Cool. So we got, what's the recoil speed? And that's what we mean by recoil, that it's then moving backwards afterwards. Now, in B here, if Kim holds the rifle tightly, like I was describing before, then her body and the rifle itself will move together, and the recoil speed is less. Explain why this is true, and calculate the new recoil speed, assuming the girl has a mass of 48 grams. By what factor is the velocity increased or decreased? Okay, so let's go and we'll look at section B here, and we could draw another picture, but I think you probably get the idea that she's just holding on. Well, maybe I'll just draw it a little bit. That she's just holding on to that thing real loosely here. Let's see if I can draw a fast one here. And so now here's going to be like her shoulder. Oh gosh, how do I draw a shoulder? That's going to be like her hand. And so then this is going to be like butted right up against her shoulder there. Oh gosh. And then her other hand is like coming up over here. Okay. But I think you get the idea. It's like, she and the gun are now moving as one. Well, all the same, tricks that we did before or understandings that we understood before must be true. So I'll keep my system both well, now I'm actually going to change the system just slightly here, because if the gun and her are one thing, then the gun and her, wait, did she have a name? Kim. Gun and Kim are like one thing there, and then plus the bullet. So now I'm going to put her in the system because now she's moving and she's having some momentum and such like that. So I, again, am including everything that's interacting here in my system. And so I know that the change of momentum still must be 0, and the momentum beforehand must be equal to the momentum afterwards. And now, whenever I'm thinking about the gun, it's really just the gun and Kim. So now let's think about that. Hey, what's the mass of the gun and Kim there? And so, well, that's 2 kilograms for the gun and 48 kilograms for Kim there. So that's a total of 50 kilograms. So now I can just think about that as one thing. I don't have to write it as 2 separate things if I know that they're going to be moving together. And so now I go, oh, the momentum of the gun Kim beforehand plus the momentum of the bullet beforehand. We know that both of those are 0. And then afterwards, the gun Kim system has some momentum, maybe, and the bullet probably has some momentum, as we saw before. We know that both of these are 0 beforehand, and so then what's going on afterwards? Well, it's just going to be the mass of this thing times its velocity of the gun Kim system there. Plus, we already know what this is. The bullet isn't going to be changing how fast it's coming out because I'm holding onto it differently. And so this, I'm going to use the same calculation we did before, is going to be the 0.15 kilograms meters per second. So now I know what this thing is. So I'll go ahead and do that to the side there, and you could do it within here as well, but I'm kind of running out of room there. So I know that this term right here for the gun Kim system must be equal to the negative bit of this, because that's the only way that you can add to 0. So I know that the negative 0.15 is equal to my 50 kilograms times some velocity of the gun and Kim. I go and divide by 50 there, and oh, I gotta grab a calculator. Hold on, let me pause this real. And I'm back. Okay, so negative 0.15 divided by 50 now, and I get negative 0.003, and again, that's meters per second. Those units work out just nicely as we showed before. And so now this is the velocity of both the gun and Kim, since they're kind of attached to each other now and they're going to be moving together. Notice that it's much less than before. Why is it much less than before? Well, look at the math. The mass of this thing is much greater when they are together. And so then if the mass is bigger, the velocity's got to be even smaller. I think it asked what factor, by what factor is the velocity increased or decreased? Well, there's a couple ways that we can go about that. But if I see that it's this, well, let me get a different color here. If I see that it's this mass that's causing this difference here, well, then I know that I can actually just look at the mass difference and see that ratio increase or decrease. So I could go, hey, let me go and look at the velocity of the gun versus we're looking at increase or decrease. In this case, it decreased, yeah. So we'll look at the velocity of the gun versus the velocity of the gun Kim system. And separately, we can go and look at the mass of the gun versus the mass of the gun Kim system there. It's supposed to be G. The pen doesn't work too well at the edge of the screen here. And if we go and do that, we get 0.003 divided by 0.075, and we get a 0.04. So we have only 4% of the original velocity that the gun had. Now Kim and the gun have that velocity. And if I do that for the mass there as well, I get almost the same value. Now it's slightly different because we're dividing by something else, but we see that this is 0.0416. And so again, it's about 4%. The gun has about 4% of the mass of the gun Kim system here, and which is why it decreased by so much there. Okay, cool. Great, that's it. Have a beautiful day.